And what I did, I had someone cleaning the windows. You know, they stand on this. So we have the scaffold. We're going to clean windows, usually attached with the rope on this end pulling upward, and a rope on that end pulling upward. So we have two ropes. This is a piece of metal, hopefully, or heavy wood there, because you're going to be standing on it. You don't want it to break and fall 10-story down, kill yourself. But you're standing on that piece of wood or metal there, attached with two ropes pulling upward. We'll call them the tension rope 1 and the tension rope 2. Assuming that board is uniform, which means the mass of it can be treated right in the middle of it. Let's give it a length. What do you want to use for a length? 4 meters? It is 4. I just want to put it somewhere else, because I got to put some pictures on the top. There we go. So it's 4 meters long. And let's assume this board or this piece here has a mass of 50 kilogram. It's a good solid piece of wood or metal there. I want to make sure it doesn't bend and fall. Now we'll put 2 guys on it here, cleaning the windows. One person standing here, and we'll say he's 1 meter from the edge, 1 meter from this edge, and has a mass of 72 kilogram. We got another one who's standing right in the center here. There's a lady. We'll put a lady here. Right at the center. Her mass is 60 kilogram. We got a bucket of water here. We're going to clean the windows, so we need some water here to clean it. Has a mass of 10 kilogram. And let's say that water is how far you want it from the edge, this edge. Pick a number. 1? Okay, 1 meter from this edge. And if the beam is stationary, it's not moving, it's not spinning there, we have what we call equilibrium, static equilibrium. If you have static equilibrium, you have 3 conditions. It says the net forces in the x direction is 0. The net forces in the y direction, the sum of them is 0. And the net torque, if you pick any point on that beam, if it's not moving, spinning, the net torque is 0. That's the 3 conditions when you have a static equilibrium. So if you have a ruler that's hanging like this and it's not moving, it's not spinning, because notice it's free to spin. If you tie a string to it, it can spin like this. The fact is not spinning, that means we have static equilibrium. Sum of the torque is 0. It's not going up and down, that means sum of the force in the y direction is 0. It's not going left to right, that means sum of the force in the x direction is 0. So let's take the beam and let's put the forces on it. I'll redraw a free body diagram. And we got tension 1 up there. And my goal is, by the way, to find what is the tension T1 and T2, how much the ropes are pulling up with, what's the value of that force. So find T1 and T2, that's what I'm looking for. So we got both of these ropes pulling upward. We got the gentleman here has a mass, so it has a weight pulling down. The weight of the first person we call weight 1, person 1. And how do you find the weight? Isn't that 72 times 9.8 mass times gravity? So 72 times 9.8. 705.6. We'll make it 706 Newton. Now in the middle of that, we get the weight of the woman, and we also get the weight of the second person, two of them. I mean the weight of the beam and the weight of the woman there. So the weight of the beam, B for beam, which equals, the mass of the beam is 50, 50 times 9.8, that's 490. That's the beam itself, the scaffold. The weight of the second person, the lady there, 60 kilogram, 60 times 9.8, 588. What else we got? The bucket of the water there. Weight of water, W. 10 times 9.8, which is what? 98. Any other forces do we have acting there? Did I leave anything out? That's my free body diagram. All the forces acting on that beam. Okay, let's apply these three conditions. Condition 1, condition 2, condition 3. It says sum of the forces in the x direction is 0. That's another way of saying all the forces, if you take all the forces pointing to the right, should equal all the forces pointing to the left. Do we have anything pointing to the right? No. Do we have anything pointing to the left? No. Can't use it here in this example. There was nothing horizontal. Okay, that's condition 1. Condition 2, sum of the forces in the y direction is 0. Or all the forces pointing upward, if you add them, they should equal all the forces pointing down. What do we have pointing upward? T1 plus T2, good. Tyler, very good. What do we have pointing down? All the weights, right? The 706, bless you, the 490, plus the 588, plus the 98. So T1 plus T2 equals what? 706 plus 490 plus 588 plus 98, which is 1882. There is one equation by how many unknowns? 2. We need a second equation by 2 unknowns. So what's the next one? Sum of the torque is 0. Or the net torque is 0. So let's look at it. Condition 3, the net torque is equal to 0. Pick any point on that beam. It really doesn't matter which one you pick. But if you want to make the math easy, you pick a point that has one of the unknowns on it. Because if I pick this point for the torque, that means this force has 0 torque. Why? Because it goes through that point. The distance, torque is force times distance. The distance from the point is 0. When you draw a parallel line, continue with this line all the way down, what is the perpendicular distance from this force to that point? 0. So this has a 0 torque. So we always pick a point that has a lot of unknowns when we calculate the torque, because all these forces, all these unknowns will disappear. So let's look at it. So we're going to take the torque at that point. We'll start with this one. Just look at that force alone. If that's the only force acting on it, is it going to make the scaffold spin clockwise or counterclockwise? This one.
Counterclockwise.
Try again.
Are you talking about weight?
So there's like, picture there's a nail here holding this, but that's free to move, right?
Oh.
And you put that weight there. Is that weight going to make it spin clockwise or counterclockwise?
Clockwise.
Clockwise, going to pull it down. It's going to move down. Don't pay attention to the rest of them, just that one alone. This will make it go clockwise. That's a negative torque. So a negative what? 98 times the distance from here to here. What's that distance? From here to there. 1 meter. This is the 2 meter from this one, right? So this force was 1 meter away from the point here. So let's look at these two. Again, these two are pulling down. So they're going to make it spin clockwise again. So we'll take the 588, should be a minus here, right? Times what? 2, but I need to have that a minus because that's clockwise. And let's take the weight of the beam itself, the 490, that's also clockwise. 490 times the 2. What about the weight of the first person? This one. Clockwise or counterclockwise? Clockwise, that's a minus 706. And how far is that person from this point?
1.
It's 1 from this one, Carol. So a 3 from this one. The whole beam is 4 meters, right? So it's 3 meters away. And what about T1? That's counterclockwise, that's positive T1. And how far T1 from this point? 4. So let's see what do we have. Negative 98 minus 588 times 2 minus 490 times 2 minus 706 times 3 equals negative 4372 plus 4T1 is equal to 0. I can finish that now. 4T1 equals what? 4372. What is T1 equal to? Divided by 4. 1093 Newton. So that cable was pulling up roughly at 1100, if I use 2 significant digits, 1100 Newton. Cable T1. Can we get what cable T2 is doing? Go to this equation. Do a substitution. T1 plus T2 equals 1882. T1 is 1093 plus T2 equals 1882. What is T2 equal to? 1882 minus 1093. 786. And if you want 2 significant digit, 790. So that's how much tension on the cables. Cable 1, this one is going to have 1100 Newton, this one's going to have 790 Newton on it. And the reason, because most of the weight on this side, notice this person is on this end, this person halfway. So this person really, if I don't have this one, they'll be equally divided for that person. But adding that person on this end is going to add more to that than this one. Let's try another one. I got it. Diving board. We got a pool. And the diving board usually looks like this. It has 2 straps somewhere to hold it. or a piece here for support, pushing up on it. So when you're standing on it, that piece pushing up. And you got another one here. You know, you attach it to a screw right here to hold it. So it's sitting on a block here. That's what it looks like, something like this, support. And we have a support right here. That's what the diving board looks like. You have two support spots there, you know. And you're standing at the end of it. Now, let's say this is a big diving board, one of those Olympic size one. The length of this is 5 meters. Okay. We're going to assume this piece, let's put it right at the end here. Otherwise I have to give you, I can put like a few inches there, but I'll put it at the end. This piece like right there at the end of it. So I don't have to use that distance. Come on. This support beam right at the edge of it like this. It's not hanging extra, right at there. The other one, from this point, let's say it's 1.5 meters from this edge. From here. So this is the 0 meter. That's 1.5, and that's the 5 meter. Let's say this person has a mass equals 90 kilogram. Now let's see what will happen. Now I'm just thinking about it, and I could be wrong. It really doesn't matter, but that's what I'm seeing. If this is the beam, if you stand right here, you have your weight down, which is mass times gravity. I'll give you a mass for that actually diving board itself. What should we use for a mass for the diving board? What do you want to use? These are like not heavy ones. You've probably seen these diving board. It looks like maybe the mass of the board is, I don't know, 20 kilogram. It's not that heavy. So the mass of the person is 90. Gravity is 9.8. What's 90 times 9.8? That's equal to 882. At the end, that's at the 5 meter mark. If this is the 0 meters here, we have the weight of the board itself, halfway. This is the 2.5, assume it's uniform. The weight of the board equals what? The mass of the board, 20 times 9.8, that's 196. Now what about this one? I'm thinking here, if you're standing on this, what's going to happen? If this is the ruler, then I get two pieces here. If I put some weight on that end, what's going to happen to this end? Watch the one in my left hand. It's going to go up. See that? So if you're standing here, the board wants to spin like this. That means it's not going up because somebody is pushing down on this here from this end. So I think the force on this end is going to be down. We'll call it F1. I could be wrong, but it really doesn't matter. I'm trying to see what will happen. I can make the assumption any direction. And if the math comes out negative, that means my direction is wrong. And what about this one? Do you think that's up or down? Has to be up. Why? Because I've made them all going down. Up equals down. But think about it. This wants to come down. The board wants to go down, and the reason it's not going down, this is holding it. So here we go. So this one is going up here. We'll call that F2. This is the 1.5 meter. So I had F2 pushing up here. I had F1 pushing down here. Usually they have some nuts at the end there to hold it from coming up there. And again, I'm standing on that board, nothing is moving, nothing is bouncing, I'm not jumping, I'm just standing on it. We have static equilibrium, which means if I take all the force in the x direction, they should add up to 0, or there's nothing in the x direction here. Don't waste your time on it. All the force in the y direction should add up to 0. That means up equals down. What do we have pointing upward? F2. What do we have down? F1 plus what? 196 plus 882. Clean it. F2 equals what? F1 plus 196, 6, not 3, plus 882. That's one equation. And what's the third equation? Sum of the torque is equal to 0. Pick any point on that beam. And again, I usually pick a point where it makes my life easy. I don't have to recalculate. I mean, I can pick this point, but now I got to figure out how far each one from it, do extra work. Why? Why not pick this point and you have all the distance already in reference to that point? So 0 equals, let's begin with that force. That's pulling upward, so it's going to make the beam goes counterclockwise, F2 here. Counterclockwise, the torque will be positive, F2 times the distance, which is 1.5. What about this one? I already made a mistake. I put a plus, it should be what? Minus, because it's going to make it spin clockwise. 196 times the 2.5. And the weight of the person is going to make the beam wants to go down. That's a minus clockwise, 882 times the 5. 1.5 F2 minus, let's see what that number is. $4,900 is equal to 0. 1.5 F2 equals 4,900. And what is F2? 4,900 divided by 1.5. 3266. 3267 Newton. And guess what? I'm going to be wrong on F1. It's going to tell me it's pointing upward.
I figured too,
Huh?
yeah. I thought so.
Yep. But I don't really have to think about them. I can make any direction, make an assumption, and if the sign is negative, it says, oh, your direction is wrong.
Does that mean you just have to?
I don't have to redo anything, just know it's going to be going upward. That's it. That's the good thing about it. Now, can we find what F1? So I go to this equation. F2 plus equal, oh no, I was right, it's plus. It's going to be a plus here, actually. I thought it was, oh no, let's see. Yep. Equals, let's do the math on the calculator. It's too early to do it in my head. F2 is what? 3267, nope, I was right, actually, the direction. Equals F1 plus 1078. Can we get what F1 is? 9. Notice the fact it's positive, that means my direction was correct. I thought this one F2 plus F1 equals that number. That's what I was thinking is negative. So my assumption that this force is going to be pushing down, this is up, is correct. But if I got a negative value here, it says, you know what? The math is good, except this force instead of down will be up if it's negative. Yes, Amoy, go ahead.
96 times 2.5 is 490.
Which one?
900.
Which one?
96 times 2.5.
Plus that number.
Okay.
I did both numbers together.
All right.
So if you go here, Amoy, 196 times 2.5 plus 882 times the 5. That's where the 4,900 came from. It's,
How did you like assume that F1 was going down?
well, I'm just picturing this in my head. If I'm standing this, if this is balanced here, and you stand on this, right? Where is that end going to go? If I stand on it, it's going to go up. The fact that that end didn't go up, that means what? Somebody was pushing down on it to keep it from going up. So that's why I made the assumption it's going down. But for you, you don't have to worry about it.
No.
Just make it direction, any direction you want it to be.
Just curious.
Yep. Because sometimes the problem gets a little bit ugly. You go, which way is it? Like, I'll give you one. Another one. Let's take this example. You want to paint a room in your house. This is the wall, and you want to paint it. This is the floor. And you take a ladder, you put the ladder there. There's my ladder. The ladder is 13 feet long. Lucky number. This ladder, I think 13, is that 12 and 5? 5 feet here to make a Pythagorean theorem, and that's 12 feet. I don't think I need these, but I'm just picturing. Because that c squared equals a squared plus b squared. 13 squared is 169. 12 squared plus 5 squared is that? Yep. So it'll be 5, 12, and 13. If it's at 5 feet here, you had it 5 feet back and 12 feet up. I don't think it matters. Well, I shouldn't say I don't think it matters, but we'll see what will happen. You want to paint a spot on the wall there. So the ladder has a mass. The mass of the ladder, let's pick a number for it. What do you want to use for a massive ladder? 10? Okay. 10 kilogram. You climbing the ladder. You're standing on the ladder here. There's you. Not way at the top there, so you're down there a little bit. Your mass here, this is dying here, 80 kilogram. And we have to find out how high are you on the ladder. Obviously, you're not 12 feet up high. I can give you what the distance here if you want to. Or I can go the height here. Let's say I'll do this distance here. So your weight straight down. Your weight is coming down, right? So let's say this distance right here, from the red line to here, I'll just give you that, 4 feet. You stand there. Hopefully you got on the ladder those plastic ends so the ladder doesn't slide. Otherwise, if this is slippery, what will happen to that ladder? It's going to fly backward. So the ladder wants to go backward if it's slippery, but what's keeping it from going backward this way?
The wall?
Well, the floor, right? So the floor has to be gripping on it. If you put the ladder on a slippery floor, it's going to slide backward, like this. The fact it didn't slide, that means somebody probably was pulling in this direction. And we have no idea what that value is. Let's call it fx. Also, why didn't the ladder go through the, straight down through the, if this was a piece of paper, the ladder on a piece of paper, what will happen? We'll put a hole through that piece of paper. It will fall down, right? The fact it didn't put a hole in the floor, that means there was a force pushing upward on it in that direction. We'll call it Fy. I have no idea what the value is. Let's assume this side here, it's really smooth. Otherwise, we're looking for trouble here. The wall is very smooth wall. What is that purpose of the word smooth here? No friction up and down. It's not going to push up and down on me. But the fact you're leaning that against the wall, that means the wall was pushing in this direction on you. If the wall wasn't pushing, that ladder will continue moving forward and fall on the ground. So these are the forces on the ladder. All the forces. Everyone see them? So I want to calculate what f of x, f of y, and p. All these forces, I want to know. How big are they? Find f of x, f of y, and p. All three. Free body diagram. Here we go. That's the ladder. I got f of x this way. I got f of y that way. Yeah. I get p this way. I get the weight of the person straight down. I'll draw a dotted line here. The weight of the person, which is what? The mass of the person, which is 80 times 9.8. 784. How about the ladder itself? It's going to have a weight of the ladder right here. And what's the weight of the ladder? 10 times 9.8, 98, correct. Anything else? Doesn't look like it, right? Okay. Here's the first condition. All the forces in the x direction, the net force should be 0. Or right equals left. What do we have pointing to the right? F of x. What do we have pointing to the left? P. One equation, two unknowns. Sum of the forces in the y direction is 0. In the y direction, what do we have? Up equals down. Up we have Fy. I shouldn't say Fy and Fy here. See, that gets confusing. But this Fy has nothing to do with that Fy, you know? So Fy, that's going up there. What do we have pointing down? 198 plus 784. So we know what that ground pushing up there. Fy now equals what? Is it 90?
982, yeah.
982, thank you. So we're done with this piece. We found one answer. So we got a third of a point on the homework for this question. 3 parts. Find f of x, f of y, and p. We found f of y. The next one is sum of the torque is 0. And you always want to pick a point that has a lot of unknowns. And this is a good spot that has 2 unknowns. This and that. They'll disappear. The torque by these will be 0. Remember, the torque is the force times the distance to the pivot point. That's perpendicular. Distance that's perpendicular. So if I extend this force, the pushing force, if I extend it, will look like this. What is the perpendicular distance from that point to that force? That will be that distance. P is pushing in this direction. That's the distance that's perpendicular to P, from here to there, which is in this case will be what? Isn't that 12 feet, the height of the ladder? And it's going to make the ladder spin which way? Counterclockwise. See, going counterclockwise when you push on it? So that's positive P times the distance, which is 12. Let's look at the 784. It's pulling down, will make the ladder go clockwise. That's a negative 784. And I need to know the distance that's perpendicular, which means that distance. What is the distance from here to there? Well, the way I drew the picture, that distance is what? 4 feet. Minus the 198 times the distance from here to there.
Would you have to convert feet to meters?
All these I think in feet. So as long as I stay with the units here, I'll be okay, mathematically. Because I'm using feet, 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 so mathematically they cancel each other out. But if you want to be, like in physics, correct in physics, the distance should be in meter, but in terms of the math, you'll be okay. And you're right, because this is, we do the weight, you know, the mass times the 9.8 meter per second squared. But in terms of the math itself, if you convert these to meters, all of them in feet, you'll be fine. As long as in every one of them, because the same conversion factor. So what is the distance from here to there? I need to know what that distance. How can I find that?
Just assume it's 2.5.
Well, we have to assume it's 2.5 here. This is the 2.5. Oh, I'm sorry. What's that in feet? This is 13. So what's half 13 at 2.5? What's half 13? 6.5. That's a 6.5 from here to there. We need to find what that distance is. So let me go to the side and see if I can find the distance. Let me look at the first picture. The first one, which is the ladder leaning like this. Right? We had the ladder leaning. This was 12. We said this one 5. This one 13. Can I find what this angle is? Theta. What's that angle theta? I can use any of the trig identity. I can say sine theta. Sine is what? Opposite over what? Hypotenuse. Can I get theta? It's the inverse sine of 12 over 13. So let's go to your calculator and get what that angle is. Second sine 12 divided by 13. 67.4. So the ladder makes a 67.4 degree angle there. Now, let's look at the second part of that. That angle didn't change, right? That angle is still 67.4. We said this distance is what? 6.5. Can I find that distance x now? Which trig identity will allow me to find that distance? Cosine, that's the adjacent over the hypotenuse. which means x equals what? 6.5 times cosine 67.4. Let's see if, Mike, if you were right. You said halfway through that. Let's see if it is. Take the cosine of that, multiply it by the 6.5, and what do you know? 2.5. Half of that distance. Halfway through, half the distance. But instead of wondering if it is 2.5 or not, we showed you the math. And it says, oh yeah, that is 2.5. Because the ladder, the mass of the ladder is halfway through the point. So this would have to be halfway the whole thing. So let's look at that. That's 198 times what? The distance, which is 2.5. And how many unknowns do you see there? One unknown. If you multiply these two numbers and move them to the right side, they'll become positive. And let's see what these numbers, 784. I got 3631, which means P equals, divide that by 12, 303 roughly. And what is f of x? 303 Newton. All of my numbers, they were two significant digits. So to make that two significant digits, you write that what? You can't write 300 because 300 will make it what? One significant digit. So what you have to do, make it 3.0 times 10 to the second. And this will be 3.0 times 10 to the second Newton. Two significant digits here, 980 Newton. So we know what Fy, Fx, and P. And you can draw pictures after pictures, story, change them. I'll do one more. Different example. What should we do? I got it. We'll take a person actually holding a weight. Jonathan, here we go. I'm gonna give you one for you. Do we have, I'm trying for the dimension of a person there. I don't have a dimension of human here. Well, there's one. Somebody holding a sign. See this one, it says stop. So you got, oh boy, here we go. So if you're into the health field, you probably know all these muscles, or physical fitness here. You're holding a sign. The sign has a mass. The person's hand also has a mass. Now, it looks like that's the radius, which is the mass of the bone right there. You got the humerus right there, has a mass there too. You got this muscle pulling up. You got these forces, the joint, and we have no idea if they're pushing up or down. So we have different parts, actually different muscles that are acting on you there. And the question is probably find what is this muscle here, the deltoid muscle, how big it is, and what's the joint doing here on you, if we know what these masses are. That looks like a good problem here. So let's write what we know. I'm assuming this is what, the fat around the bone, the radius, the meat?
No, those are just two different bones.
The two different bones?
Yep.
Okay. What about the meat itself? You know, you get the skin there, the muscle.
They just don't have it labeled.
Yep. So I guess they're not paying attention to it. Maybe the person is dead. We're dealing with a skeleton here. Okay, that sounds better. But now they have no muscle there if they're dead. So this is what we see. Crossing guard holds a stop sign, arm length. Her arm is horizontal. That's what they say in the problem here. I don't know if you can see it. I'm just reading the problem on the left side. The arm is horizontal. And we assume that the deltoid muscle is the only muscle supporting her arm. The weight of her upper arm is, that's WU, this guy here, is 18 Newton. That's 18, I'll just put it here. They give me that in the problem, so when I switch to it, I'll have all the numbers. The weight of her lower arm, W1, is 11 Newton. So they're giving us the weight of the whole thing here. Newton. The weight of her hand, WH, is 4 Newton. And the weight of the sign is 8.9 Newton. WS is 8.9 Newton. The location where each of these forces acts on the arm is indicated in the figure. So the distance right there was given to us in the bottom. So we're going to use these distances. A force of magnitude FD, that's the deltoid muscle up there, is exerted on the humerus by the deltoid and the shoulder joint. Exerts a force on the humerus. We have two things. We have the joint here, has F of X and F of Y, and we have the deltoid. And the angle the deltoid makes is 18 degrees. And the question says, is the magnitude of F of deltoid, F of D, greater than, less than, or equal to F of X? Well, we're going to find them anywhere. Then we can answer all the questions. So let's draw that one. You saw the picture here. So this is what we have. I'll put the hand as a stick like this. Well, first I'll do the hand like this. There's the hand holding the sign. Then the arm gets bigger. And there's the joint right here. And we have a value in this direction. They call that F of X. And they draw an arrow pointing upward. We're not sure if it's upward or down. It's called F of Y. The deltoid muscle here pulling back, they're called F of D. The angle here is 18 degrees. That angle here is 18 degrees. We have the thicker section of your arm has a weight of 18 Newton. The skinny section here of your arm has a weight of 11 Newton. The hand has a weight of 4 Newton. And also the sign that you're holding as a stop has a weight of 8.9 Newton. And the question, find FD, Fx, and Fy. I'll put the dimension in a second here. They're in the bottom here. I'll put them there once I do the free body diagram. So this just again, an arm holding a weight or holding roughly here 1 pound, no more than 1 pound actually, 1 kilogram, almost 1 kilogram, like 2 pounds. You're holding it 2 pounds like this, holding it, the sign weighs 2 pounds, and your arm stays horizontally. So this is what we have. Free body diagram. The weight of the hand, which is 4 Newton. Should give myself some room. The weight of the sign, 8.9 Newton.
Do you want the paper, Lizzie?
I should plan to give me more space there, but wasn't thinking. The weight of the lower part of your arm, 11 Newton. The weight of the upper part of your arm, the fat section, 18 Newton. The deltoid muscle on an angle like this, I'm making the angle bigger so I can put the angle there. FD, the angle is 18. You got the joint here, on it there's 2 forces, F of X and F of Y. Notice this force actually, it's not 90-degree angle with this, so I'm going to break it down to X and Y components. So if I break it down to X and Y components, and I'll deal with the rest after, one more free body diagram. Give me some room here. I have down in this direction the combination of both of these, the 4 and the 8.9, which is what? 12.9 when you add them both? And the distance, by the way, from this point, I'm going to give you the distance now. The distance was given to us from that in that one to be 65 centimeters or 0.65 meters from the joint, from here. We got the 11 Newton down. And the distance, the 11 Newton, given to us to be 42 centimeters or 0.42 meters. The fat section of your arm, 18 Newton. And the distance happens to be also 18 centimeters, which is 0.18 meters. Now I'm going to take the FD and break it down into 2 components. It's going to have a component in this direction. It's going to have a component in that direction. And the mark here, this is at 14 centimeters. So what is the component in the Y direction? Upward. What's that value equal to? Isn't that FD times what? Sine of 18 degrees. And what's the value in the X direction? FD cosine of the 18 degrees. That's supposed to be 18. And the last 2 are what? F of X, F of Y. So I took that deltoid muscle, I broke it down to X and Y component. Notice I took these 2, put them together to make it one force. 12.9, 4 plus 8.9, 12.9, instead of listing each one separate. And now if my arm is horizontal, I'm holding the sign, so stop, don't move. I'm holding that sign, we have static equilibrium, which means all the forces in the X direction have to add up to a 0. That implies if you take all the forces pointing to the right, should equal all the forces pointing to the left. What do we have pointing to the right? F of X. What do we have pointing to the left? FD cosine 18 degrees. Cosine 18 is a number, we can figure that is. Condition 2, all the forces pointing upward. If you add them, should be 0. Or all the forces pointing upward should equal all the forces pointing down. Upward, what do we have? We have f of y. We have f of d sine of 18 degrees. What else do we have pointing upward? Is that it? What is pointing down? 18, 11, 12.9. 18, 20, 30, 40. Is it 41.9? I think it's 41.9. I should double check it. I don't want to do it, find out later that number was wrong. That's my second equation. So I have two equations by how many unknowns? 3 unknowns. That's even worse. $41.9, yep. The last one, sum of the torque is 0. And I'm going to pick this point, and the reason I'm choosing that point, because now this will be 0, this will be 0, and that will be 0. Any force that goes through the pivot point will have 0 torque. So I don't have to deal with this, this, or that. So let's look and see. FD sine 18 is going to make it spin which way? Counterclockwise, that's positive torque. And the distance is 0.14. The rest of them, the other 3, is going to be spinning which way? Clockwise, that's negative torque. 18 times 0.18, 11 times 0.42, all negative. I should be negative here, not positive. And the last one, 12.9 times what? 0.65. Do the math. Take these numbers, multiply them, move them to the right side, they become positive. On the right side, I get 16.245. On the left side, because I multiply them and I move them there, they became positive. What is sine 18 times 0.14? That's 0.043 FD. Can we get what FD equal to? 16.245 divided by that number, 375 Newton. Now if I know FD, can I find the rest of them? Do you know what f of x now? If you know FD? Sure. What's f of x going to equal to? F of x is going to equal 375 cosine 18 from the first equation, from this one. 375 times the cosine of 18 degrees, approximately 357. Can I get f of y? Right here. This equation. F of y plus 375 sine 18 equals 41.9. Let's see, 375 times sine 18. It's 115. So when I take it to that side, f of y is going to be a negative number. Negative 74. That says, guess what? Your direction for f of y, instead of pushing down or pushing up, is going to be what? Pushing really down. Well, if you think about it, if that's the ruler, if you attach any weight, what's the weight? It's going to tip backward. That piece is going to go upward. So when you push down, this wants to go upward. So the reason it's not going upward, the joint is pushing down on it there. That's why it didn't go up. If you lift it up there, stop pulling up there, it wants to go down now. So the reason it's not going down, the joint is pushing up on it. But again, I don't have to worry about, is it up, is it down? Just make an assumption and go through the math. If the value is negative, your direction is wrong, it's backward. If the value is positive, your direction is good. You know? You don't have to go back and redo any of the work there. It just says your direction is going to be going in the opposite direction for this one.